Hello viewers. In today's presentation, we are going to discuss moment of inertia. We are familiar with the concept of linear inertia. It is the tendency of a body to resist its linear velocity. That is, objects do not change their state of linear motion unless acted upon by some net external force. In the case of rotational motion, an object's tendency to resist change in its angular velocity is called rotational inertia or moment of inertia. In the first example, we can see a car is moving with some initial velocity u in a straight line, and as soon as brakes are applied after covering some distance, the car comes to a standstill. If no brakes are applied and we neglect the effect of frictional forces, then the car should have been moving with its initial velocity throughout the path. This example represents the concept of linear inertia. In the next example, the blades of a fan are in a circular motion. If the electricity is turned off, the rotational motion of the blades do not stop instantaneously. Rather, it continues its motion for some time before becoming completely stopped due to air resistance, bearing friction, etc. This tendency of continuing in rotational motion when no external torque is applied is termed as moment of inertia. In an ideal case, if we can make air resistance and bearing friction negligible, then the fan should be continuing its rotational motion with uniform angular velocity forever. As definition, the moment of inertia of a body about an axis is the measure of the difficulty in starting or stopping or changing the body's rotation about that axis. So far, we have described the moment of inertia qualitatively. To present the moment of inertia in a quantitative way, we have to begin with the concept of rotational kinetic energy. Suppose a rigid body rotating about a vertical axis with an angular velocity omega. Let us also assume the body is made up of a large number of small particles of masses m1, m2, m3 situated at perpendicular distances r1, r2, r3 from the axis. As the body rotates, each particle of this body follows a circular path around the axis. Although each particle of the object has the same angular velocity, they have different linear velocity based on their distances from the axis of rotation. Total rotational kinetic energy can be obtained by summing up the rotational kinetic energy of individual particles, that is, Tr equal to half of sum over I equal to 1 to n mi Ri square times omega. If we compare this expression with the kinetic energy expression for translational motion, then it can be said that the effect of mass in translational motion is portrayed by the term sum over I equal to 1 to n mi Ri square in rotational motion. This term sum over I equal to 1 to n mi Ri square is the moment of inertia of the object. Thus, the moment of inertia of a rigid body rotating about an axis is the sum of the product of the masses of its particles and the square of the perpendicular distances from the axis of rotation. Moment of inertia of an object is directly proportional to its mass distribution, and the axis about which the object is rotating. Now, let us introduce radius of gyration. Suppose an object of mass m is rotating about an axis with angular velocity omega. Now, if we can fix a distance from the axis at which if the whole mass of the object can be concentrated so that the moment of inertia would be the same as with the object, then that particular distance is termed as the radius of gyration. By equating the total moment of inertia in summation form with what we have got from the concept of the radius of gyration, we can obtain an expression for the radius of gyration. The radius of gyration of an object about an axis is defined as the root mean square distance of the particles of the body from the axis of rotation. Now, let us obtain an expression relating torque and moment of inertia. Suppose an object is rotating around a vertical axis. Let a constant angular acceleration is produced under the action of a torque tau. The body is made of a large number of small particles of masses m1, m2, m3 situated at perpendicular distances r1, r2, r3 respectively from the axis. If we focus on any particular particle, say ith particle, then the linear acceleration of the particle can be expressed as ai equal to ri times alpha. If Fi be the net external force acting on the ith particle, then Fi equal to mi ai, which is mi ri times alpha. Therefore, the magnitude of the torque on the particle is going to be tau I equal to Fi times Ri, which is equal to mi Ri square times alpha. By right hand thumb rule, it is seen that torques on all the particles acts in the same direction. Therefore, the net torque can be obtained by summing up the torques of all the individual particles, that is tau equal to sum over I equal to 1 to n mi Ri square times alpha. Therefore, torque is equal to the moment of inertia times angular acceleration. Both torque and angular acceleration are vector quantities and are having the same direction. Similarly, starting from the concept of linear velocity, we can obtain an expression relating angular momentum and moment of inertia, which is L equal to I times omega. Both angular momentum and angular velocity are vector quantities and are having the same direction, which can be obtained using right hand thumb rule. We can also relate torque and angular momentum using these expressions. Let us begin with the expression for angular momentum in terms of moment of inertia, that is L equal to I times omega. Differentiating this equation with respect to time, we get dl dt equal to I times alpha, which is equal to tau or torque. Hence, torque is the time derivative of angular momentum. From the above expression, we can say if no external torque is applied on rotating object, then its angular momentum must be conserved, which means moment of inertia times angular velocity should remain conserved. Using this principle, we can explain when a freely rotating object pulls mass closer to the axis of rotation, why its angular velocity increases. As an example, let us consider the case of an ice skater. When she stretches her body, she actually increases the moment of inertia around the axis of rotation. As soon as she pulls her all body weight closer to the axis of rotation to reduce the moment of inertia, the conservation of angular momentum law comes into action. If angular momentum has to be conserved, then the product of the moment of inertia with angular velocity must remain conserved. As moment of inertia in the second case reduced, which results in increasing in angular velocity of the skater. Two very important theorems are associated with moment of inertia. These are parallel axis theorem and perpendicular axis theorem. Parallel axis theorem states that the moment of inertia of a rigid body about any given axis is equal to its moment of inertia about a parallel axis passing through its center of mass plus the product of the mass of the body and the square of the perpendicular distance between the two parallel axes. Perpendicular axis theorem states that the moment of inertia of a plane body about an axis perpendicular to its plane is equal to the sum of the moment of inertia of the plane body about any two mutually perpendicular axes in the plane of the body which intersects the first axis. Moment of inertia of some common shapes with respect to the axis of rotation is shown here. Now moving towards the problem of rolling cylinder without slipping over an inclined plane. The force diagram of the problem is shown in the adjacent figure. Forces along the x and y axis can be equated easily from the figure. Now, for rotational motion about the center of mass, the only force that produces the torque is the frictional force. Therefore, tau equal to Fr times r, that is radius of the cylinder. Again, tau equal to I times alpha, that is I times a by r. Here, a stands for the linear acceleration of the cylinder, which means Fs equal to Ia by r square. Now, moment of inertia for a cylinder about its axis is half of mr square. Putting these values in the force equation along x direction, we can estimate the value of linear acceleration A with which the cylinder is moving down the inclined plane. A equal to 2 by 3 g sin theta. Here, theta is the angle of inclination of the inclined plane. It suggests all the rolling solid cylinders have the same linear acceleration down the inclined plane. We can also estimate the minimum coefficient for static friction required for pure rolling using these equations, which is 1/3 of the tangent of the angle of inclination of the inclined plane. To summarize, in this chapter we have discussed the concepts of moment of inertia, obtained a relation with torque and angular momentum, saw some examples of regularly shaped objects' moment of inertia, and finally discussed the rolling motion without slipping over an inclined plane.